Great, thank you. It's great to be here. I regret I can't be here in person for the full few months. It would really be a great experience, but I'm going to come in and out as I can. I'm going to talk today about the evolution of gravitational wave data analysis computing, really from a Ligo perspective, or Ligo Virgo Couvares perspective. This is a tricky audience because I don't know what you're interested in, and I don't know what you already know, and so I aim for a little bit of breadth. But if there's places you want to go for depth, let me know, and I'm happy to talk more about things or follow up afterwards. First, I'm going to talk a little about who am I. I have some background in LIGO science, but I think between Barry's talk and some of what Marco went over, I can skip past a bit of that. I'm going to give some background on gravitational wave data analysis computing, talk a bit about optimization, very broadly defined, and briefly touch on some challenges facing gravitational wave computing. So who am I? I'm kind of an odd duck in this world. I started in industry, actually, in the 90s, and then moved into research at UW-Madison as part of the H.T. Condor project. Worked there for a decade, went back to industry briefly, and then found my way to LIGO, and now I'm at Caltech. I manage the LIGO data analysis computing and lead the LSC's optimization effort, again, sort of broadly defined, and I'll say more about what that means. Why am I here? Because I was invited, but the reason I want to be here is to meet you all, to get to know you, and to build relationships for the coming decade of gravitational wave research that you're all going to be involved in, or many of you will be involved in. There's a number of research computing challenges that LIGO, Virgo, and Couvares have in common. There's distributed job and workflow scheduling, the kinds of things that H.T. Condor does, which is actually a very hard problem. The sort of evolving intersection of high-performance computing, traditionally defined, big, very expensive machines with really fast interconnects between individual nodes, often the sort of leading edge of the processors, et cetera, and high-throughput computing, which is often done on sort of the sweet spot and the price point of commodity Intel hardware. And the idea is you just want as many CPUs as you can get for the dollar and run your computations on that. And for a long time, those two worlds were sort of disjoint computing worlds, and they are merging like two black holes. And it's very interesting, the things that are happening there. There's a lot of challenges around GPUs and multi-core optimization. For a very long time, everyone could write codes that were targeted at individual cores and just kind of, and generic Intel instruction sets, and just kind of ride the wave of faster and faster processors. And as you all know, the individual clock speed of individual cores is more or less flat, and what you get now is lots more of them, and that's a real challenge, not just for individuals writing their codes, but collaborations managing entire suites of codes. There's distributed computing challenges that are very specific to large scientific collaborations that you don't have when you're an individual scientist or a small group, a small team. There's problems that are very distinct at that human scale. And finally, one challenge that we're grappling with is how to apply machine learning, which is sort of transforming a lot of data science to gravitational wave data analysis problems. And really what I want to do is to share what I know, learn from you, and find collaborators for future work. This is just the stock photo of LIGO. Let's see. I think it's notable. I'm actually really proud to be here 6 years ago today. It is the anniversary of our landmark gravitational wave. And if I can just share a little anecdote, one of the things I sort of forget about that was so fun about this when it happened is that nobody in the collaboration believed it was real when it first happened, or very few people did. If somebody tells you they thought it was real, they're probably lying, because we had a policy of blind injections where a very small team of people were, for more than a decade, a few times a year would inject signals into our data secretly, so that we would always be finding gravitational wave signals, and it would remove that bias where humans would find a signal and you'd really want it to be real and you'd kind of cheat. So there were always signals in our data, and then we'd find out a few months later that they were fake. And so this this signal was it was beautiful. It was much louder and clearer than we had hoped for, and so it took between days and weeks for the entire collaboration to sort of be convinced it was real. And it was really a fun few weeks where we were all arguing with each other about whether this was a double-blind injection. The collaboration came out and said, no, this wasn't a blind injection, this is real. Nobody believed them. People are like, oh, this is trying to see what's going to happen if they tell us it's a real injection. It was great. So that all started 6 years ago today, so I'll never forget the process there. Just a reminder on what is the network we're talking about. There's a new name that's getting used more and more for this, which is IGWIN, the International Gravitational-Wave Observatory Network. It's being used more and more in the computing context, but I think you'll start to hear it more and more in the science context as well, because we can't just keep adding a letter every time we add a detector, or the acronym will get very long. So I still say LVK for LIGO, Virgo, Couvares sometimes, but I'll also intermix IGWIN. I'm inconsistent in my usage. But this is IGWIN. It's the two LIGO observatories, which is the button for the, there we go. The two LIGO observatories, the smaller GEO detector, Virgo, Couvares under construction, and LIGO India soon to be under construction. This is what I'm going to skip through because you all know it. What can gravitational waves tell us about the universe? Why is this important? This is worth reprising, even though you've heard it, which is there's four astrophysics groups in LIGO and Virgo. There's the burst group, which looks for unmodeled sources. The CBC group, compact binary coalescence group, which looks for modeled signals. There's the continuous wave group. And then there's the stochastic group looking for the stochastic gravitational wave background. Each group proposes its own science goals, determines its own algorithms, and writes the applications and runs them. There's also this sort of fifth group, which isn't a source, it doesn't correspond to a source, but the detector characterization work, which supports the commissioning teams and astrophysics groups and does all the work that Marco was talking about this morning. And that is a computational consumer and drives a lot of computation in the collaboration as well. So from a computing point of view, you can almost think of that as a fifth search group. And each of these groups has diverse teams, algorithms, and methods, and they lead to very heterogeneous demands on our computing infrastructure. LIGO, for those of you who are familiar with the high-energy physics world, LIGO is much less structured, much less centralized. There's a lot more independence in sort of computing that has evolved over the years. And so we have a really diverse mix of codes, frameworks, approaches, and that leads to a real challenge. Broadly speaking, computational cost goes up, signal duration goes up, and this is where the four lie. So you've got compact binaries. The CBC group traditionally has been very computationally expensive to their searches. Very short signals. Continuous waves are long signals and expensive. Bursts are cheaper and shorter, and SGWB is cheaper and longer. And detector characterization kind of sits there at the bottom. This is some of what I can skip. It's worth mentioning that especially in 01, and to some degree even now, one of the things driving the computational cost of our CBC search, our flagship CBC searches, is our template banks, and this gets to how we generate waveforms. And one thing I just want to highlight here is that when we put together a template bank of waveforms to match against the data, we lay out these template banks to be dense enough such that less than 1% of signals have an SNR loss greater than 3%. And so in practice, that means we have about 1 million templates in a template bank. And since every chunk of time series data from the detector has to be compared to every template, that drives a lot of our computational costs, or has in the past. It's also worth mentioning that would be bad enough if we didn't have noise and the need to generate statistical significance. But we do time slides where we take... Yes?
How long are these intervals that we do?
The chunks? It varies, but depending on the analysis and the observing run, it's been tweaked over time, but typically 20, 48 seconds, 40, 96 seconds, something like that.
And so it varies means depends upon what?
Well, so you can, if it's a choice made by data analysts that there's trade-offs between the computational cost and how much of a signal can fit within each chunk. And so, for longer signals, you pay a price. For shorter signals, you want it to be as short as it can in some sense, but
because in the templates they have various lengths.
Exactly. Yes. The time slides is how we estimate the background, and so what we do, maybe you're all familiar with this already, but we simply take the data coming out of each detector and shift it in time by more than the maximum light travel between the two detectors, so that if you shift the data from the two detectors by 10 seconds, and you get what we think is a coincidence in the two of them, it has to be a noise coincidence. And so by doing that, and we do 1 million time slides, we generate a background and can say that an actual event is louder than any noise. It's 1 in a million, against the noise coincidence. And so you can see here, for example, this was our flagship detection. These are all the noise coincidences. So these are how many of those artifacts that Marco couldn't remove happened in coincidence with one another in two detectors. And a detection statistic is essentially think of it as a fancy signal to noise. And so they basically fall off at about 20. That's the most, and the signal was way above the noise, and this is how we can tell that we've seen a signal and not just accidentally had a blip in two detectors at the same time. I mention this only to emphasize that really drives a lot of the computational costs, because you're doing the whole search a million times on each of these time-shifted data sets. So our requirements of computing are really to analyze data in unison from this worldwide network of detectors, to reduce the background, and to enhance the scientific output. This breaks down into two kinds of analysis. There's the low latency analysis and the computing infrastructure that supports that, which is trying to come up with a detection in seconds to minutes after the data comes out of the detector. And then there's the offline infrastructure, which can take hours to months to really do the deep analysis. The low latency data analysis infrastructure now includes rapid parameter estimation to try and characterize the signals, verification, automated follow-up, and like I said, we have less and less. This is my question to Marco. How often do the humans still need to be in the loop? And they do, but our goal is to get them out of the loop more and more. The offline infrastructure. One other thing I'll say is in 01, this low latency analysis infrastructure was much less important than the offline analysis, because we hadn't detected gravitational waves before, and coming up with the 5 sigma conclusive detection of the first gravitational wave was the prime directive of the collaboration. Once that had been done, actually coming up with signals quick and guiding telescopes became much more important. The offline infrastructure uses detector characterization feedback to do a much better job with data quality than the latency analysis can. Deeper and broader searches for transients, and then there's the continuous and stochastic searches in there, and then better and better parameter estimation, et cetera. Notably out of scope for LIGO and Virgo computing is numerical relativity simulation. We use NR waveforms to test our template banks, et cetera, but we don't. LIGO doesn't organize or do the computing to actually do those simulations. Groups do that on their own and then collaborate with us. And before 01, the line between what's NR computing and what's LIGO computing was bright and clear, and it's getting blurrier over time as we have more and more NR people in the collaboration. But the computing needed to do those big simulations is not part of what we do. Our data analysis computing architecture is this is a little diagram. We have the actual physical hardware, data centers, and facility. On top of that, actual clusters and operating systems, storage infrastructure, networks. On top of that, we have engineering and operations infrastructure, which is monitoring, support, automated build and test work, packaging, things like HT Condor, workflow management, higher level cluster automation. We have what's called collaboration support, which is very important to the science of LIGO and Virgo, but it's not data analysis computing. It's things like single sign-on for the 150 wikis we have. In the bad old days prior to 2007, you needed a login at every individual wiki and every individual bug tracking system and every individual cluster. And when you've got 2,000 people and potentially 400 services, it's completely unmanageable. And so managing just basic functions of the collaboration, like having a single sign-on infrastructure, identity and access management, collaboration services to manage the MOUs of the various groups, all of this, you can almost think of it as back office computing for a giant collaboration, is a big chunk of what we have to do. Then there's data handling services. This is the infrastructure that actually transports the data in low latency and in bulk. So there's 2 different sets of infrastructure, one streaming for the low latency searches and one to actually transfer the data, the permanent data sets around to big clusters so that we can do deep analyses. There's data federation, data quality infrastructure. Marco talked about all those channels and the vetoes that we generate that searches consume so they know when not to analyze the data. All of that infrastructure is part of this. The candidate event infrastructure, where we actually store candidate events and communicate them to the broader community, all that kind of stuff. Then there's application building blocks. This is basically any code, data analysis code, that's common across more than one search. So we have, so everybody's not rewriting the same code to open a frame file and read the data. We have common I/O libraries. We have common, even things like waveform generation. Anything that more than one search has to do, we try and get into this common infrastructure here. So there's an enormous amount of that. And then there's actual individual search pipelines and applications. And these are usually written by small groups, often in one institution or a small number of institutions collaborating. And these are the actual searches and the parameter estimation codes, et cetera. The demand for our computing is driven by about 90 different searches or analyses. And so across those 4 search groups and detector characterization, there's about 90 different searches we do. And each one, there's about 60 different software pipelines implementing them. So there's a few pieces of software that drive 2 or 3 or 4 or 5 different searches. But it's almost one piece of code per science target. And so there's a lot of software. And this is the software in the top box here. That doesn't include any of this stuff, but just this box here. There's 60 codes and 90 searches.
What is the software pipeline?
Sorry?
What is a software pipeline?
Sorry, good question. A software pipeline is the process of actually doing a search is a careful orchestration between code that needs to find the data, bring the data to where the computing is, open it, often there'll be a first pass. A different search will do a first pass. It'll then store some intermediate data files, run a bunch of other codes on it. At the end, it might put together, run codes that generate LaTeX or HTML so that people can see the results of the search. And the orchestrated workflow of multiple individual pieces of code that have data passed between them, we call it a pipeline, because it's kind of a pipeline throughout, pipeline or a workflow. Does that answer your question? Interestingly, the distribution of computing demand in terms of the number of cycles, about 10 pipelines of these actually this should say 10 searches, but 10 searches, and it probably is 10 pipelines as well, drive about 80% of our demand. And then there's a long tail. So we have a small number of searches that are very computationally expensive, and then a bunch that are much less so. But interestingly, the distribution of data analysis, computing, engineering support effort, the FTEs that are needed to support this are flat. In other words, it takes about the same amount of computing infrastructure and optimization support for every one of these as each other. I mean, they're all roughly the same. And so they have very different demands in terms of their CPU cost, but in terms of their human cost, they're very similar. Just to give you a sense of scale, our data rates, we generate about 3 gigabytes a year of H of T strain data. And so, by big data standards, Ligo is very, very small. I mean, this was about the same 20 years ago, and 20 years ago, this was a lot, right? So in 2003, Ligo could call itself, a big data project. Not so much anymore. I mean, this is a very small amount of data. We generate about, do I have that down here? I don't have that on here, but petabytes a year if you include all the environmental channels. Now those don't go out beyond the observatories, but even that, petabytes a year is not a lot of data these days. I mean, it's not simple, but it's not a lot of data. We have a normalized unit of computing called an MSU, which is millions of service units. We borrowed that term from Exceed, the Supercomputing Consortium. A service unit is a CPU core hour on a very particular processor, which is now like 8 years old. And a million of those is in it. So an SU is 1 CPU core hour on that CPU. MSU is a million. In 2004, we projected to need about a billion service units, so about 1,000 million service units. So about a billion CPU core hours on these processors. We have about, of the sort of 2,000 people in the collaboration, roughly 3,000, I can't keep track anymore. We have about 600 people who use the collaboration's computing infrastructure, and about 300 of them active at one time. These are old numbers. They might be bigger by a factor of 1.5 or something, but it's roughly, a third of the collaboration does computing, and about half of that are active at any one time. But again, just like the pipelines, about 20 people drive about 70% of our entire computing demand.
So Gone have their own supercomputers. Does Ligo have something similar?
So, by supercomputer, I presume you mean a sort of traditional high-performance computing with a fast, InfiniBand and fast interconnect. I'll get to some of the resources we have later, but LIGO, other than the LIGO laboratory, LIGO doesn't own any computing. The laboratory has a significant amount, but computing is contributed by groups within the LSC and Virgo and a lot of outside shared computing that we use. And I'll go into a little more detail about that later, so ask me later if I don't answer that question well. We also have, those 90 searches are prioritized. This is kind of, for those of you who know the joke about Lake Wobegon, where all the kids are above average, we have a similar naming scheme. There's not high, medium, and low. There's highest priority science, high priority science, and additional priority science. But the bulk of our science is categorized as the highest priority. About 78% of our computing demand. But every search has to be prioritized in one of these categories. And the motivation for this, I'll talk a little bit more about later, but this really was we never did this before 2014, 2015, but it was a mandate from the NSF so that if we made a mistake and ran out of computing and came to the NSF and begged for more money for more computing, they want to know that we actually had some idea of what we could cut first. If push came to shove, what we had to do and what we could leave on the table. So the bulk of our searches are embarrassingly parallel. This phrase has changed over the years. Sometimes people want to call it pleasingly parallel. It's a computer science term. It just means computational problems that you can sort of arbitrarily slice into smaller pieces and can be computed independently on different machines without coordination. Almost everything we do is embarrassingly parallel, with some small exceptions that I may mention later. That's a huge advantage in computing. That's why we can use what we call high throughput computing, which is commodity clusters without fast interconnects. You can use much cheaper hardware when you're doing embarrassingly parallel computing. When you're doing simulations, things like that, MPI codes, you need very different clusters that cost a lot more money, even if they're very similar architectures, because you need those fast interconnects. And so the cost of high throughput clusters can be anywhere from a quarter to a tenth the cost of the HPC clusters. All of our analyses and computing resources are managed using HT Condor. There is an asterisk there. There's some, for lack of a better word, sort of legacy resources that came in through Virgo that are still running their own local batch systems. But everything that we support sort of formally, centrally through LIGO computing staff and infrastructure and Virgo computing staff and infrastructure now is managed using HT Condor. So HT Condor is a batch system. It's a piece of code that you run on a cluster that allows you to queue up jobs, queue up work, and it reliably executes them in the cluster so that if a node goes down and your job failed, it reruns it automatically. You don't have to think about it. You submit 1,000 jobs, you come back in the morning, they're done. At the simplest level, that's what it does for a single cluster. It also extends to multiple clusters and it helps manage the complexities of running small pieces of code at a very large scale and tries to insulate users from the pain that you would go through if you had to SSH into every machine and run it by hand and deal with the failures. The sort of standardization on this platform for job management and job submission has turned out to be very important for LIGO because the common tools have really allowed us to just save a lot of time and effort. Everyone learns the same language. You can all communicate efficiently. And again, in the bad old days when there were 8 different batch systems and some people were using something called PBS and some people were using LSF and some people were using some grid engine, you'd go to a different cluster, you wouldn't know how to do your work. You'd have to learn it all over again. We'd need staff who had expertise in 4 different systems. This is just a platform standardization. But it's more than that. And that's what I was going to get to at the bottom of this slide, which is the LIGO's relationship with the team that runs this, which I used to work on, is very long and deep and unusual. We have weekly meetings between senior staff in each project. I've had that for more than a decade. When LIGO or Virgo has a computing problem that in any way intersects with HT Condor, they're on it right away, and we have a bug fix, in 24 hours, 48 hours. All hands are on deck to fix it, and we probably get better support from this research project than we do from any commercial vendor we've paid any amount of money in 20 years. It's a great relationship, and it's kind of a real aid to our science. HT Condor also provides something called the Directed Acyclic Graph Manager, DAGMAN, which does for for workflows, for collections of interdependent jobs, what Condor does for individual jobs. In other words, if you've got a chain of 14 different things that have to happen in a specific order, and something fails in the middle, you don't want to have to start it over again. And DAGMAN ensures that if there's a failure in the middle, it can restart the entire workflow in such a way that when you come back in the morning, it's done, and you don't have to deal with the fact that it failed halfway and the data didn't make it back to the home base, et cetera. And this is particularly important because our workflows can have up to 10 million jobs. We have about the biggest workflows of any user of Condor, and that includes CMS and Atlas and LHCb and big high energy physics experiments. LIGO has very complicated workflows with a lot of moving pieces, and DAGMAN manages all that. So we also use something called the Pegasus workflow management system that worries about data dependencies in addition to job dependencies. So you don't just have a DAG of job dependencies, but knows a little bit more about the data. Most of our workflows don't use that, but I mention it here because it's an important piece of infrastructure for some pipelines. And so notably, these tools also have helped us move from exclusively internal resources. Again, up until even less than 10 years ago, but let's say 10 years ago, all of LIGO's computing was done on computers either owned by the LIGO laboratory at Caltech or by 3 or 4 major LSE groups. UW-Milwaukee had a big cluster, but all of that hardware was internal to LIGO, and that's not true anymore. And we wouldn't have been able to make that transition as easily without this computing infrastructure. These are our major data centers that LIGO or LIGO groups own and manage. There's the largest ones at Caltech. There's large ones at each Detector, Livingston and Hanford. There's one at UW-Milwaukee, large one at Cardiff. Growing computing resources at IUCAA in India. There's something called the OSGRAV collaboration that has a lot of computing resources. And then there's 3 large Virgo clusters in Italy, France, and at NICEF. But one thing that's worth noting is since the beginning of 2001, it's about 90% of all the computing we've done has been provided by LIGO resources and about 10% by Virgo. And this has been an issue in the collaborations because in principle there should be, in fact it's written into the MOUs, there should be contributions proportionate to the number of authors. And so Virgo should be contributing about 1/3 of the computing resources. This was almost zero 6, 7, 8 years ago. And so actually this is a huge improvement, and the progress there. Virgo really is committed to bringing this up now, but it's still, right now, the computing is largely driven by LIGO. In fact, yeah, here's a breakdown of our supply. So we have many types of supply of resources, and this is answering your question from earlier. We have dedicated resources, which is what, all of these I would call dedicated or allocated resources. So either we manage the clusters ourselves, or there's a huge cluster like CNAF, and we have an allocation on it. There's also opportunistic resources. And so our dedicated LIGO lab and LSC clusters still constitute about 80% of our supply. But that's down from 100% just a few years ago, or close to 100%. In this other 20% are the Virgo clusters and allocations, clusters at LIGO India. Sometimes PIs of individual LIGO groups, as part of their startup, you get a big cluster. Those are not insignificant. Some of those are high. Sorry, I should have said the Virgo clusters are mostly high throughput clusters. LIGO India clusters are mostly high performance clusters, so they were built for MPI. They're big, expensive clusters. We use them for high throughput work. PIs have clusters, campuses, and sort of regional consortiums have shared clusters that we've resourced to. There's national shared supercomputers, for example, Exceed, Blue Waters. We have opportunistic cycles, so there's campuses that have spare cycles that we piggyback on when they're not doing local work. DOE labs, high energy physics clusters, we get a lot of what we call backfill. So there's idle moments in those clusters, and we can run gravitational-wave jobs on them. And we have the technical capability to also use commercial cloud resources, but that's not currently part of our funding model, so it's not something we do in production. But essentially, they look like these resources. What's important about this is that this red box, and this is all we did until 5 or 10 years ago, is very easy to manage this kind of computing because you build your own clusters. You can make them all look the same. You make them just the way you want. You can set them up to be very easy for data analysts to use. They log in and all their software's there. Everything, just all the gravitational wave data's there. Everything's easy. When you're using somebody else's computers, and moreover, you're using 14 different sort of kinds of computers. They might be high-performance clusters that are shared by 1,000 people. They might be a PI's local clusters. They're all different. They all have different logins. They all have different software installed, different versions of Linux. They might not have your data. They might have some of your data. Making these useful to the entire collaboration without consuming a tremendous amount of staff FTE time is actually a huge challenge, and I'll get to that in a minute. And so our computing environment is getting more and more complicated. This is sort of, again, I told you how Ligo, most of Ligo's workflows are high throughput and can be run on very cheap commodity machines. Up until about 2014, our view of high HPC resources is that, that's a Ferrari. We don't, HPC centers are Ferraris, and this is what we need. We need an army of Yugos, not a Ferrari. But as I said, there's been this blending of the HPC and HTC world, both in terms of their goals, but also there's been a shotgun marriage. I mean, the NSF was very clear around 2014 and 15 that HPC centers needed to start serving major projects like Ligo, and Ligo needed to be able to use HPC centers and not say, we just give us money, we'll build our own clusters. The NSF at some point said, listen, we're making an investment in these supercomputing centers. We want you to use those for your sort of peak demand. We're not going to give you another $1 million to build a bigger cluster. And likewise said to the computing centers, why aren't you helping Ligo do their science? And so we tried to figure out how to get a Yugo into stick a Yugo on top of a Ferrari. And we ended up, compromising on a fleet of Porsches. Like I said, we adopted this high throughput computing model about 20 years ago, and HT Condor. And there's this newer organization called the Open Science Grid that's more recent, but is sort of anchored on the same philosophy and culture and some of the same software as HT Condor. And in fact, this isn't really important, but they've just merged last year into a single project. So these aren't even independent projects anymore. But the NSF's view is that there really has to be a close coupling of computer science and domain science. And this is a group that's kind of leading that and supports us, and we support them. But there's a lot of other computer science research that can be useful to gravitational wave science, and finding a way to integrate CS research into a production physics operation is a real challenge. And so I encourage people who have ideas on ways we can do that to talk to me. So some of our, let me look at how I'm doing. How am I doing on time? I don't have a clock.
We have about an hour left.
Great. Okay.
Let's say 45 minutes.
Perfect. So some of our opportunities and challenges, we've got to integrate and build up the infrastructure in Virgo and Kagra, the computing infrastructure. Ligo India is being commissioned soon, and the computing infrastructure is already being stood up. We have more and more international gravitational wave partners, KISTI, which is a Korean effort, OSGRAV in Australia. There's more and more HPC centers we're working with. Again, these are just some of them. Individual LVK groups, and the cloud, of course. This I've already covered. Virgo resources have been tapped really for the first time in 2003 at scale, but still under computes. Kagra at the moment has almost no funding for computing and basically contributes nothing to Ligo Virgo Kagra computing. The Kagra's contribution, Kagra's worried about building a detector right now and getting it commissioned, and to some degree, contributing to the data analysis software effort, but infrastructure, there's no contribution from Virgo yet. Long term, that's obviously a challenge for us because the NSF doesn't want to necessarily subsidize Virgo and Kagra indefinitely in terms of computing. I mentioned some of these things because these funding issues, certainly, obviously, but the political issues around that, can turn out to be extraordinarily important in the computing, as important as some of the scientific or technical issues. And so the computing decisions that get made as a consequence of these facts influence all kinds of stuff, and I'll talk more about that. But this turns out to be important for the science. We've had allocations on HPC centers in Exceed that have been very successful, Stampede and Comet in particular, particularly for the CBC computing. But it's been hampered in the past by the complexities of moving data between shared computing. So we still have enough, a full rerun on 03 might need 30 gigabytes of gravitational wave strain data. And that's not something that's hosted at a given exceed cluster, and that's a bit more than you can sort of stream in on demand if you're just running there for a day. And so we've got to stage these big data sets to a cluster before we run on it, or we've got to build up networks to the point where we can stream 30 gigabytes of data to 10,000 cores and not take down the network. And this sort of distributed, doing the compute and data co-scheduling on distributed resources is a major focus of our optimization efforts right now in order to use these heterogeneous distributed resources. And again, this is how the Open Science Grid is very helpful for us. I talked about how you have all these different clusters. They all have their different versions of Linux, different software installed, different data. What OSG does, in a sense, is it's a universal adapter to other computing resources. They're very good at providing a very small, portable software stack that a systems administrator of a local cluster can kind of plop down and give us a consistent bridge to that resource, such that our users don't need to know the vagaries of what's unique about those clusters. And so we can now run on all of these different clusters we don't have to worry about a lot of the details of what they do differently. Users don't need to worry about that. The sites don't need to worry about what Ligo needs. They just OSG is the glue that holds this all together and kind of provides some standard plumbing. And it's been extraordinarily valuable. We couldn't have moved beyond our internal infrastructure to this complicated heterogeneous infrastructure without that organization. And OSG is an interesting thing because it's both a software stack. It's a bunch of infrastructure software that manages these batch systems and data movement. But it's also a collection of people that provide expert help. They're really sort of domain experts in heterogeneous computing and distributed computing. And so they're very helpful in hand-holding individual cluster administrators into working with us and in getting our codes running on them. And OSG really came out of the high-energy physics world. The LHC experiments needed it for the same reason we do before we did, and evolved OSG. And we were a late, maybe not a late, but we were the sort of second wave of science experiments to use OSG. OSG is very, very good because they don't get hung up on boundaries and processes. It's not that, you very rarely, when you ask for help solving a problem, you don't get the answer, oh, that's not our job. Our wall stops here. They kind of dive in and go over the walls to help us with things that maybe we should be responsible for if they know how to fix it. And same things with the site administrators. And they're very good at just solving the problem and not worrying about whether it should be their problem or not. And that's that's a cultural bias of that organization that's very rare, especially in the computing world. Computer scientists are very bad about being flexible. So when I say it's a universal adapter to lots of different computing resources, this is just a selection of, 6 months. This is even 4 or 5 years ago, but it gives you a sense of the diversity. Each one of these colors is a different cluster. None of these clusters are ours. These are all somebody else's clusters. They're all different. And over this period, this was our usage of them. So you can see both how incredibly bursty our usage of these shared resources is, and how diverse. It's not like 90% of it came from one big cluster. We take what we can get, and so we get an enormous amount of computing from an enormous amount of different providers. And what allows this to happen is this universal adapter of the Open Science Grid. I talked a lot about how OSG helps LIGO already. One of the things I didn't say is we also get a lot of benefit because they can generalize the experiences of other large and small scientific research projects. So the lessons that LHC learned the hard way, LIGO benefits from. The lessons that LIGO learns the hard way, LHC benefits from. And there's really a consolidation of lessons flowing through OSG, and that's been as valuable as the infrastructure. Now, why is LIGO valuable to OSG? This is more about why OSG is valuable to LIGO. We've used about 65 million CPU core hours, et cetera, et cetera. They host some data for us, et cetera, et cetera. We're good for OSG because it broadens the community. It's not good for OSG to really just be a computing center for high-energy physics. They really want to be serving the entire scientific community and have made that transition over the past 5 years or so. And LIGO was one of the first big users that extended OSG beyond high-energy physics. LIGO brings a lot of new human and computing resources to OSG. LIGO has traditionally been on the cutting edge of a lot of what the NSF calls cyber infrastructure, but sort of computing infrastructure, and has driven a lot of the software that OSG now uses. Ligo brings a lot of expertise. This is some of the distributed identity and access management. We did a lot of the single sign-on work for big collaborations long before other big experiments did. OSG helped us bring that out to other people. And we're also a good, we're a guinea pig. We're willing to help them test new software and new approaches that other projects wouldn't, because we trust them and have a good working relationship and know that they're not going to leave us high and dry.
So what would be the next big users of this OSG?
Well, so things like IceCube, LSST, which is now, remind me the new name for LSST. Vera Wang Observatory, is that the, no, not Vera Wang. There's a, LSST has a new name. It's been named after, anyway, never mind. Lots of, so in the kind of astro space, there's a lot of experiments. And then more and more, OSG has tried to support very small scientists who can't afford the computing infrastructure of large experiments. In some sense, what they do is they solve computing problems for large experiments in order to manage an infrastructure that small scientists can come to. And so there's something called OSG Connect. If you don't have a cluster, you don't even have a node that you can use to kind of visualize your data on. There's sort of it's a community resource. And they've gone, I think now they have thousands of PIs using this, people with very, very small grants. And so they support everything from some of the large LHC and astro experiments to a lot of the broader scientific community. And they have a lot of bio users now that I couldn't even tell you what the experiments are, but there's less so in the, I think the NIH still kind of does its own thing. I don't think there's a lot of NIH research flowing through the open science grid, but DOE, NSF funded projects, a lot of them use OSG now. Yeah, I think I've said enough about this. So, one of the reasons we want to work not just through OSG with HPC centers, but directly with HPC centers, is that we really want to be prepared to scale quickly if we need to. So, what in the computer world we call elasticity. So, if you have 1,000 computers that your baseline demand is 1,000 computers all the time, but twice a year you need 10,000 computers for 6 hours. You obviously can't build a 10,000 CPU cluster. You can't justify that. But you want relationships with big clusters so that you have an agreement that if we raise the flag and need 10,000 cores for 24 hours, can you provide it for us? And do we have the infrastructure to get the jobs out there? And we want to do that. We want to leverage. There's a lot of expertise at high performance computing centers that really doesn't exist anywhere else, particularly for code optimization. Exceed employs a small army of people who know how to optimize code better than most individual scientists. And I have a lot of good stories about that too, because as you all know, physicists are famous for thinking they can do things better than other people. How hard can it be? I can optimize my code. And very often we have people who swear their code is as well optimized as it could possibly be. And then we have them talk to an optimization expert at TAC in UT Austin or something for a few days, and they double the speed of the code in 2 months. I mean, there's often optimizations people don't even understand they can do. And HPC centers is where that expertise lives. And also, as I said, the evolving high throughput and high performance computing world, how these things are funded, what the scope of these centers are, who they serve, is evolving rapidly. And if we don't have good relationships with those centers, and we don't know them and what they need, that evolution is going to happen without LIGO's input and may not happen in the way we need it to. So being connected to that community is very important to make sure we're a part of it 5 years from now, 10 years from now. So I mentioned earlier about how it's more complicated now to write code that uses many cores whose individual performance isn't increasing. That's only one of the ways in which computing, large-scale data analysis computing in a big experiment is getting much more complicated. Is going to get much more complicated over the next 10 years than it has over the past 10 years. And this slide is about why. So there's much more heterogeneity of processing hardware. 10 years ago, you pretty much could target Intel x86 code and be done with it. Now, if your code can run 5 times faster, 10 times faster, 100 times faster on a GPU, you've got to write code for a GPU. Nobody's going to give you funding to run on a CPU if you can run 100 times faster on a GPU. But it's really hard to write code to run fast on a GPU. And worse, much worse, is that CPU code that you wrote in 1993 can run now on the modern hardware. GPU code, you write code for a GPU now, it's not going to run on GPUs in 5 years. You're going to have to rewrite it every 3, 4, 5, 6, 7 years. And it's becoming more and more true for a lot of these multiprocessor environments. And so without realizing it, we're very accustomed to a world in which, and the funding agencies are accustomed to a world in which code needs to be, there's new codes that need to be written all the time, but old codes will continue to work. And that's really not true. If you want optimization now, you also have to have this sort of regeneration every few years. And that's very, very expensive. Many integrated cores. It's an Intel. It's Intel lingo for an architecture they tried to sell for a few years and have actually given up on. But it's shorthand for something that looks like an x86 processor, but has instead of having an 8-core or 24-core system, you might have something that has 200 very slow Pentium cores. Was in fact what they really did. They used a 12-year-old architecture, but put 200 of them on a chip, and so you're not writing GPU code, you're writing x86, but you've got 200 slow cores on a CPU instead of 16 fast ones or 8 fast ones, and you have to do different things to write code for that. And so again, this really big problem is that you have to rewrite these codes, and so the cost of software development and software sustainability, which is sort of a buzzword, which is how to keep a piece of software continuing to run robustly over the course of years when the people who wrote it may disappear and get other jobs, and how to do that is getting much more expensive. There's an increasing heterogeneity of providers. Like I said, instead of just up until not that long ago, big projects, the NSF, the DOE, NIH would give you money, you'd build your own cluster, you'd run your code, and that doesn't happen anymore. Now they say, go use that supercomputing center, go use that cluster, use the OSG. And so you have these heterogeneous resources, and it's a nightmare to manage. It's a necessity, but it's a nightmare. Heterogeneity of software environments. There's now, again, if you run your own machine, you decide what operating system it runs, but we now run, there's 14 different flavors of Linux we have to support. There's containers, there's virtual machines, all of which you kind of have to know you're running on, especially if you're trying to optimize your code. And there's things like containers help mitigate this, but don't solve that problem. Again, there's heterogeneity of batch and queuing systems. OSG solves that problem for us. And we just interface with HD Condor and don't care if the actual cluster is running something different. But this is a problem for OSG and for anybody who's not using OSG. Increasing heterogeneity of storage and network interfaces and capabilities. Every country and project and large consortium has a different way of organizing and moving data around. And it's very difficult when you start working with a different group to figure out how to manage data. Policies for access and identity management and workflow prioritization. Every provider's got its own idea of how jobs ought to be scheduled and provided, and that it's very hard to get work done predictably when you have this kind of heterogeneity of those policies. Accounting, which is the most boring thing in the world, but is absolutely critical because you have to tell the NSF how many cycles did we use and on what, how many will we need next time, and things like GPDR, GDPR, I forget which GPDR, I think, the new European privacy law, which provides very strong privacy protections for individuals and what kind of data organizations can keep and distribute about them, turns out to have completely broken our accounting system because clusters in Europe can't send us a list of users and how many CPU cores they used on what jobs. They need to anonymize that. And first of all, just writing code to anonymize that data can sometimes be difficult. But then once you get the anonymized data, it doesn't answer the questions we need to know, which is, how much work did we do on this problem or that problem? Often we use people as a proxy for that. We know that, Susan runs this code and Joe runs that code. And so now we have to build an extra layer of metadata that we now need to ship around with our jobs and get back, and it's a nightmare. I mean, it's an enormous amount of work. This is a whole new piece of computing infrastructure you need to do science, like Ligo. And then finally, and this is the most interesting for me, there's increasing heterogeneity of motivations and expectations. Sometimes it's mutual scientific interest. We all want to detect gravitational waves. Sometimes it's very strategic. You've got HPC centers that don't want to lose their funding. They don't really care about high throughput jobs. They want to run sexy simulations, but they need to work with you. Sometimes they really want to help. You've got, sometimes people care about scientific recognition. Sometimes it's really PR with the funding agencies. Sometimes all people care about is money. That's certainly true of the cloud. And very little of these motivations and expectations are encoded in a memorandum of understanding or a service level agreement or a contract. You kind of have to know. You have to keep track of why are these people working with us? Why are they going to want to work with us tomorrow? What do we have to do? What's going to happen if they, if the funding agencies shift? How is that going to blow apart the landscape of computing we work with? This has become a major, part of what we have to think about. It's a long-term challenge. So it's just gotten really hard to do computing at scale compared to what the LHC or Ligo was doing 10 years ago. And that's a function of how much more computing resources we need and the funding agencies recognizing that they can save a lot of money by not just handing out cash to build clusters. They can get a lot more science done by moving us towards this kind of environment, but it comes with headaches. So with that being said, I'm going to talk a little bit about optimization. So Ligo has a computing optimization project that I was brought in to lead. We have a dedicated staff at the lab and some degree from the LSC devoted to this. At one point or another, we've had the developer of every single Ligo search pipeline engaged in this effort. It has regular attention from the LSC and computing management. And over the past 7 years, we've forged good working relationships with, as I said, there's sort of these 90 searches, 60 pipelines. Each one is written and managed by and large, often by a single LSC group or a small group of them. We've had to kind of get to know and work with every one of these groups, and successfully optimized enough of our codes that we have kind of a roadmap for how to do this. This project, again, came out of the mandate from the NSF. We had a computing crisis in 2014 where, without going into all the gory details, NSF came and asked Ligo, how much computing are you going to need in 2015, 16, 18? Some people did a back of the napkin estimation, gave the NSF a really big number. NSF said, whoa, that's bigger than we thought. Can you tell us a little more about what you need, why you need this big number? And at the time, to be frank, Ligo's response was, trust us, we know what we're doing. You don't need to know the details. And that sparked, the NSF said, oh, really? Well, let's get a panel of experts to come in and see if that's true. And so, they opened the hood and parachuted in a bunch of computer scientists to look at our codes and how efficient they were. And of course, like I said earlier, we thought we were doing a great job and we're running very efficiently, and we weren't. There were opportunities all over the place to do things better and faster. And so, this project was sort of spawned from that exercise. And so now it's sort of baked into everything we do that we have to make sure we're doing things efficiently enough that if we ask for more money, the NSF will take us seriously. And we've been successful at that, but that's what this project is. That's the mandate of this project. So part of this is what a lot of people, particularly sort of programmers and software developers, think of is high performance computing, sort of floating point operations per second optimization. When you think optimization, you think the hot loop inside your code. Can I make that run faster? And that's a big part of optimization. So algorithmic optimizations, but there's also things like scientific optimization. So can we rethink? If the goal is to do this as efficiently as possible, can we make some small compromise in the science to have a huge outsized effect on the computation, and then get 3 times more resources by being slightly less sensitive in this one case and make it up later. So it's sort of taking a critical look at some of the scientific assumptions that went into a search can often be more fruitful than just diving in and trying to optimize the code. Compiler optimizations, a lot of what, some of the embarrassments we had when people came in and looked at what we were doing is we were just, compile with GCC-03, which is sort of telling the GCC is a compiler and it tells it, make this as fast as you can. Well, it turns out Intel has a compiler, and when you're running on an Intel processor, just switching to an Intel compiler sometimes can have a tremendous, they do a better job optimizing code for their chips in special cases. And that sounds simple, and it is, but we weren't doing it, and so making sure we're doing that thing. Again, writing for the native instruction set of a processor. So different generations of processors have their own, you can write assembly code tuned to that processor. You can get huge performance improvements by doing that sometimes, But again, that then incurs the future cost of having to rewrite it because it's not going to run as fast on processors 5 years from now. So you can save a tremendous amount of computing resources today, but you have a labor cost you're signing up for in the future by doing that. Vectorization, SIMD, I won't go into all these details. Again, multi-threading, a lot of our codes are written to run on a single core, and we assume at 16-core processors, really 16 one-core processors, right? But if you treat it as a whole and worry about the common cache that all of those 16 cores share, you can sometimes get tremendous speed improvements. And so when do we write codes that are designed to run on an entire socket as opposed to a core? And then, as I said, GPU and mic acceleration. And so all of these are important. And so, I guess, like I said, as a result of this, we had these dramatic optimizations. Our flagship CBC search in 2014, this is how many millions of service units. So this is millions of CPU core hours on that reference platform. Our estimate in 2014 was that we were going to need 115 million CPU core hours. We ended up, after this optimization, estimating we needed 5. In 02, going from 3, over the course of 01 to 03, we went from needing 1.4 billion CPU core hours to 177 million. That's an order of magnitude, which is on one hand a great success, right? It's also embarrassing because you shouldn't be able to have that level of optimization unless you were doing something wrong. And the low latency search also had huge gains. So there's about a factor of 8 reduction in the demand of the online search, factor of 6 in the offline search. Sorry, other way around. The offline search factor of 8, the low latency search factor of 6. And actually, I don't have the numbers handy in a table for this talk, but over the subsequent 5 or 6 years, we've achieved almost another order of magnitude improvement. And so, in fact, what I said at the beginning of this talk, that the match filter search for CBC signals, which is kind of our flagship search, was the most expensive search we had in 01. It's actually now, it's like the 6th most expensive search we have. It's not actually an optimization target anymore because it's not that expensive. Yes?
All this work about the optimization was done only by people from the collaboration or also by experts?
So that's a great question. So the right way to answer that question is to say, we would never have done this had we not worked with people in Exceed, in particular at the Texas Advanced Computing Center, TAC, at UT Austin. But they didn't do it for us. So they basically showed us what we were doing wrong. And then we realized, we have to open the hood and look for other places. I mean, they basically came up with just a few examples of what we were doing wrong. We then took that, and people inside the LSC and Ligo found the 100 other cases like that and optimized them. So we did it, but they deserve half the credit, even though they didn't do the optimizations, if that makes sense. Parameter estimation. So this is, as the cost of the CBC search, finding the signal in the data, has gone way down, the cost of parameter estimation is growing tremendously because suddenly we have signals, right? Before it was, we have no signals, we need to find one. Now it's, oh my God, the detector is, 04, we're going to be getting a ping every few minutes. I mean, there's signals coming in constantly. And parameter estimation, the cost of that scales with the number of detections, whereas the search just scales with time and sensitivity. And so as our detectors get more and more sensitive, our parameter estimation costs are exploding. And so figuring that out has become a real challenge and is now our number one focus of our optimization effort. We have a sort of transition from the flagship code we've used so far for this to a newer code. And this slide is just to say, I mean, part of what we have to, this is sort of, very, a lot of what I want to get across in this talk is a lot of the things we have to do to actually have an impact on the science they're computing optimizations, they're very technical, but the decisions about what to do are, the very boring decisions turn out to be some of the most consequential ones. Like, do we spend, we have, let's say we have 3 FTEs for the next 2 years to optimize codes in Ligo, to just focus on optimizing codes. Do we focus on optimizing the code we're going to use, we used in 01, 02, and 03, and are going to use probably and trust the most in 04, or do we use this new code that probably by 05 is going to be the new code? So in other words, do we optimize 04 and get quick results, or do we let that code run slower for the next few years and focus these FTEs on the code we're probably going to be using 5 years in the future. In the end, we kind of split the difference, and we're sort of trying to do both. But these kinds of decisions have real scientific impact. This is just saying. I want to give some quick examples of what it looks like to optimize these things. This is a profile of the LAL inference code, the parameters estimation code. This is basically what's called a call stack. So this is like your main function, if you know C, and you sort of call another function, that calls a function, that calls a function, and this is the stack of functions you call, and how long they took. The x-axis is time, and you can see that there's like 17% of the total execution of this code was spent in this trigonomic functions. It turns out these were calculations of sine and cosine of polarization angle that were within a loop over frequency, but that computation doesn't depend on the frequency. So we were performing the same computation multiple times, could have just performed it once at the beginning and saved the result. Sounds easy, but these kinds of things are very hard to find in legacy codes. Here we found that 12% of our time was spent initializing a cubic spline, but again, it was independent of the proposed parameter point, so we can just calculate it once ever and write it in the header file of the C and eliminate all this computation. Another 12% was spent in a binary search. Again, we'd only need to do it once. We're doing it multiple times. To enable some of this testing, we had to build these hardware test stands. So we have a CPU test bed at Caltech where we bought one of 14 different CPUs that people might need to run on, including the bleeding edge ones that cost a fortune but will probably be cheap in 5 years, and so that people can actually log into them and try and tune their code on it and see, or even just run, again, the Intel compiler and see. One of the things we're trying to do is get bang for the buck, and we've discovered cases where the Intel compiler, for whatever reason, can optimize, just without you having to do any work, can optimize your code particularly well on this one CPU. And so that influences our next cluster purchase. To the extent that we have 200 grand to spend on a Ligo lab cluster in 2 years, it in fact turned out a few years ago we had one particular processor that we got effectively a free optimization on that doubled the science we could do for the dollar. And so that drove which processor we picked. Whereas before we would have just benchmarked some, what looked to be the fastest. But we had a particular code that we could sort of use to do that. Anyway, so we had to build these test stands of all these diverse machines so people can do this testing and do trade studies, different clock speeds, different parallelism, et cetera. We have the same thing for GPUs. This is actually an old chart, so this is the last generation of GPUs we had in this test lab. But we have 20 different GPUs set up at Caltech, so people can benchmark their code and run on them and see what happens. And we keep track of. It turns out a lot of GPU codes, the more you optimize them, the more often you end up limited by the memory bandwidth inside the GPU, not the host to bus bandwidth, but the inside the GPU, how GPU cores to GPU memory. And so it turns out that's the figure of merit for some of our, again, it comes down to sort of science per dollar. And so we ended up for our last huge GPU purchase, we ended up buying the cheapest consumer GPUs we can find, because they had almost, they had half the memory bandwidth or a third the memory bandwidth of the really expensive ones for a tenth the price. And so we got tremendous value, but we needed to test all these to find that out. We almost never buy the GPUs that are intended for science, these expensive double precision GPUs from AMD. They cost, from NVIDIA rather, they cost $4,000, and in the end, they're 4 times faster than a $200 GPU. So we build, these are the kinds of things we have to figure out. GPU acceleration is tricky because you can do, there's sort of 3 levels of optimization you can do. There's a naive offloading, which is the easiest thing. You can just use a numerical library that knows how to run on the GPU, and you often get a 1.5, 2x speed up. Great. That's sometimes what you ought to do. But if you actually write your own code to run on the GPU, sometimes you can get like you sort of offload a particular part of your code to the GPU. You get like a 10x speed up. But you're limited because you got to kind of schlep all your data from the CPU to the GPU. That's really slow. Then you do this really fast computation on the GPU, and then you got to schlep your data back to the CPU. And that ends up, even if the GPU computation were instant, you're limited by that. So then the next step is you move your entire computation to the GPU, even the parts that don't get faster on the GPU, just so that you can not do that schlepping back and forth, except at the very beginning and very end of the job. That turns out to be incredibly labor intensive for software developers. And so, we've only done that for really one of our pipelines that was incredibly expensive because the 3 FTE years of software development effort we needed to put into that saved, 40 million CPU core hours per year, and it was an easy trade. But you've got to do this with this weird math where you're sort of comparing the cost of a software developer over years to the cost of the computing that will be saved by their effort. And also, people aren't fungible, right? You can't just pick a software developer off a tree. And a physicist is most valuable doing physics, right? We don't want physicists writing code. We want physicists thinking about physics. And so you don't want always to just take a physicist and have them writing code. You want to so can we hire a software developer? Well, it turns out if software developers aren't physicists, they often are, it's very hard to get them to interact with physicists productively and write good code. We really need these hybrid roles. We need physicists who have moved into computing, or computing people who have worked side by side with physicists for 20 years and know how to work with them. And this is not an easy thing to do. And so you're doing this math of FTEs to millions of core hours over years, and you're also then having to take into account these human factors. And again, that's the central message of this entire talk is that, this sort of, we want everything to be technical, right? We want to think about optimizing code, coming up with the best algorithm, and the actual, at the scale of a collaboration, the decisions that actually have the biggest impact on the science over years are often these much trickier ones about what kind of people do we have, and what do they want to do, and how do we make the best use of their expertise. And but at the end, it all has to come down to dollars that you can communicate to the NSF, and so it's interesting. Let's see, I talked about this. These are currently our software pipelines that are running on GPUs. PyCBC is a CBC search. It drives a number of our CBC searches. Rift is a parameter estimation pipeline. Spear is a low latency CBC search. Frequency Hoff is a continuous wave search. And there's machine learning codes that run on GPUs for glitch classification. So that gets to what Marco was talking about this morning. Can we figure out a blip glitch? Blip glitch is a blip glitch faster. I don't need to go through the details of this, but talking about some of the work we did to port this code to GPUs. Again, this is trying to figure out this is just for 20 different GPUs how our code performs, and then the next graph we would present would be the cost per dollar, and that's always very different. The fastest GPU isn't always the most cost-effective GPU. Again, memory latency, not bandwidth or compute, is the limiting factor. Actually, I said bandwidth before, which is usually, at this case, it was memory latency. And so, how do we deal with that? It's not always about the fastest possible code. It's about the biggest performance improvement for a given amount of science or developer FTE effort. We have to figure out, what's the projected cost of a pipeline over the next few years. And also, a lot of this gets into, this is sort of my original area of research in computer science, is scheduling. And, how do we schedule heterogeneous resources? How do we, if we've got some jobs that want to run on an entire CPU socket, some that want to run on a single core, some that want to run on a GPU, but each GPU needs a CPU. Just scheduling work in this environment. If you do it naively, you make very poor use of your resources. And so scheduling's become a harder and harder problem as we get more and more heterogeneous. Rift is the parameter estimation pipeline I talked about running on GPUs. I won't go into a lot of detail on this, other than to say that this actually was born from Brookhaven organized a GPU hackathon. I think NVIDIA sent some GPU experts to Brookhaven for a week, and it was kind of open to the physics community. And I sort of circulated that this was happening, and a couple people went. I didn't even know they went. And as a consequence of this week at this hackathon, one of our most expensive searches became GPU optimized, and had a tremendous 20x improvement right off the bat. And I think there's more to come. And so, it's almost frustrating to me that this happened kind of by, happenstance. I sent an email of announcement to an email list, and these guys went, and I didn't know they went. I wish these things could be better organized, right? You don't want to rely on happenstance, but that's how it happens. You kind of just have to keep trying. And here's the paper if you want to read more about that implementation. Spear is the low latency CBC pipeline. This is running on about 300 servers with these very cheap consumer gaming GPUs. This is the reference for that if you want to see it. frequency Hoff. Again, I won't go into a lot of detail on that. The point is, we now have several compute-intensive pipelines using GPUs. One of these is already using GPUs in OSG, which is great. Initially, GPUs weren't easy to schedule on other people's resources, so our CPUs, we went far and wide across the world, but our GPUs we ran at home. Now we're starting to run on other people's GPUs, which is a big improvement. These are more references if you want to know more about the GPU codes. Machine learning. So this I'm going to spend not a lot of time on, but I'm going to be a little provocative, which is there are, I don't know how many, but there might be 20 groups in the LSC, maybe more. There might be 40 groups in the LSC that in their MOUs this year said they've got something going on with machine learning. There is clear success so far in detector characterization. Projects Gravity, SPY, IDQ, I probably didn't mention a bunch, for glitch detection and classification. That's the poster child for ML work in Ligo and Virgo right now. There's a subgroup, that subgroup doesn't mean anything, but there's an organized group of people in the LBC who meet and talk about machine learning on a regular basis. We have in our GPU testbed, we have these machines, these GPU machines that are particularly targeted for ML work. They're not meant for other kinds of GPU computing. And we have one of those at each observatory for people to do this work on. But this is where I want to be provocative. In detector characterization, this has been a clear win. It's been very helpful, and you're going to hear more about that, I think, on Monday. But there are no prospects right now, at least not that I know of, for any machine learning work to benefit production gravitational wave searches or parameter estimation pipelines during 04. And the reason that's provocative is you can't believe how many papers there are saying machine learning has cracked open the world of gravitational wave searches, and we can do it better and faster. And none of that has turned into anything that works in the real world and that we're planning to use or that I can see in the horizon for using. So if you're one of the people who wrote one of those papers, I'm sorry, but argue with me. Tell me why I'm wrong. But I do know that there's nothing we're about to run in production that's come out of this work. So there's a lot of flash and not a lot of results yet on the search or parameter estimation side of machine learning. And I don't know that's because there can't be. I'm not a skeptic, but I just know there's a gap right now between, I think, getting back to what are people motivated by. I think there's a lot of rewards for writing the paper and not a lot of rewards for doing the work in the salt mines of putting together a production pipeline that can implement that and test it against real data. You test it against some fake data, write a big paper and move on, right? And that's what you get rewarded for. And so there's a sort of incentive problem to actually bring these things from flashy, proof of concepts to production searches. And when it comes to optimization, to actually doing more science with less compute, it's not helping us yet. This I already touched on, practical scheduling issues we deal with. How do you deal with scheduling CPU sockets rather than cores? How do we schedule GPUs? How do we co-allocate CPU cores and GPUs, which turns out to be very complicated because every GPU code needs a certain amount of CPU and it's different for each one, and it's a pain. Containerization and virtualization works great these days for CPU jobs. It's much trickier for GPU jobs because the way that the operating system physically talks to the GPU doesn't always work with the container technology, which means if we rely on containers or virtual machines to ship jobs around, we can't do what we do for GPU jobs for CPU jobs, and we need a second entire infrastructure. And again, we have limited people, and if you need a second infrastructure, there's a huge cost to that. It can wipe out the optimization you thought you were going to get because we can't schedule the jobs that run so fast, et cetera, et cetera. And this gets to, again, the really interesting optimization challenges, in my opinion, aren't the how to make this code in a hot loop run faster. It's when does an investment in floating point operations per second start to return less than an investment where you're focusing on floating point operations per year. In other words, sometimes focusing on scheduler robustness will deliver a lot more than optimizing a piece of code. What about workflow portability? If your code can run on any resource, you can get a lot more science done for the dollar than if it can only run on a particular piece of hardware that we have in this room. It doesn't matter how it can be 10 times faster on that piece of hardware, but it doesn't matter. Maybe you should focus on making it more portable, not faster. Workflow simplicity, and these are in conflict with one another. If it takes 10 times longer to train a new grad student to work with this code, that's a huge cost to the science. So maybe it's faster, but nobody can understand it. And so, or it's portable, but that's because you've got all this, you're handling 10 different cases in your code where you could be handling one. And so how do you find that trade-off between writing something that's simple and understandable and you can train people to use and develop, and something that's fast and portable, and when the NSF is breathing down your neck in both directions? How do you have the capability to checkpoint and resume? You know, if you've got long computations that takes 2 weeks to run, if it's your computer, great, you have it run for 2 weeks and hope it doesn't crash. If you're running it in resources across the world, it's going to get interrupted. And so you've got to write code that can write its intermediate state every so often, every hour, every 10 minutes. And if it gets killed, you know, you can resume it somewhere else. And that's more work, but can unlock a tremendous amount of computing power. In fact, I think this may be one of the most important things people can do in terms of bang for the buck. How do we measure computational efficiency? You know, there's sort of actual versus peak floating point operations per second of individual pieces of code. There's how well do you utilize the CPU over the entire process. A lot of codes are very, very fast for a little while and then sit there waiting for I/O for half their time. And you've got to look at the whole process lifetime. CPU utilization over a job lifetime. In other words, if your job takes an hour to get scheduled on a node that's sitting idle waiting for it, it doesn't matter how fast it is. If your job runs really fast, but it's an hour till it gets the data it needs, that's slow. What we call good put versus bad put, which is how many good put of a job is how many seconds of CPU time ends up contributing to the successful completion of the job. So if you're checkpointing a job, if you run for 15 minutes, you checkpointed at 10 and you got interrupted, you've lost 5 minutes. And so you have 10 minutes of good put, 5 minutes of bad put in that 15-minute job. Is that how we should measure the optimization? Good put or bad put of a workflow, again, taking into account restarts of an entire workflow of 1 million jobs. Is that how we should measure optimization of, is that what we're optimizing? CPU core hours per year per science task, that's actually probably a pretty good one. Who cares about all this stuff? That's what drives the science. Or maybe it's just like science results per dollar spent on some combination of labor and hardware over a time period, so you don't get these weird incentives where you're trying to save money on the hardware, but you're pushing huge labor costs into the future. How do we think about this and reason about it with the NSF so that we don't get boxed into really stupid decisions? And so the prospect of this computational scarcity that we had in 2014 and the mandate actually forced Ligo to prioritize its science activities for the first time ever. It prompted a reorganization and realignment of all the software and infrastructure development. It uncovered all these disagreements about Ligo lab priorities versus Ligo scientific collaboration priorities. It resulted in committees getting broken up and reformed. I mean, this push ended up prompting thinking about all kinds of different scientific decision making in the collaboration, and so it had a sort of very far-reaching consequence way beyond the technical. And it was ultimately the catalyst for, but not the cause of, major changes in the LSC. So seemingly technical issues reveal non-technical issues that couple in very unexpected ways. And so, great, this is my last slide, I think. So this is what I look at for the optimization, is you look at what I call the whole patient. There's scientific prioritization and scoping, performance benchmarking, figuring out how fast are things currently, how much do they cost, so you know what to actually pay attention to for optimization. Looking first at data analysis methods and algorithms, optimizing the implementation by hand with the compiler, with the library, the workflow and robustness optimizations, development, testing, simulation process optimizations. This is interesting because sometimes we've got really fast code, but if in an observing run, we run it 7 times because every time a new calibration comes out, we rerun the entire thing. Maybe the best optimization has nothing to do with the code. It's maybe instead of running this 7 times in an observing run, we can run it every other calibration, or run it on the first 2 and the last. Suddenly we've saved 50% of our computing without touching a piece of code. Scheduling optimizations, workflow portability optimizations, in other words, run on more resources rather than run faster on the ones we have. Finding more resources. Procuring things just in time. If you spend your money at the last minute, you get better hardware. Don't buy 2 years in advance. Buy it just before the observing run. The accounting we need to do this. Again, optimization, sustainability. How do we make sure this work we've done to optimize codes isn't lost over time? Documentation, training, collaboration, external engagement. We kind of have to look at all of this. So, which of these are interesting to you, if any? Where can you help improve gravitational wave computing? I'd love to talk to any of you about this. I want to neglect nothing, focus on bang for the buck where we can be most effective, and avoid adding burden to scientists where the payback is small.
Thank you so much.